Good evening, and thanks for joining tonight's TI Technology webinar hosted by Texas Instruments, where tonight we're going to use the TI Nspire as a tool for inquiry. My name is Mike Houston, and I'm the moderator for this event. I teach algebra and calculus near Pittsburgh, where I use TI Technology to make tough-to-teach, tough-to-learn concepts accessible to all my students. I'm really excited to be joined by our two panelists tonight, Steve Phelps and Bill Carrascio. Steve, a longtime geometry teacher, currently teaches AP statistics, regular statistics, and computer science. Steve is a T-Cube national instructor and co-authored Advanced Quantitative Reasoning Mathematics for the World Around Us, presenting quantitative literacy, statistics, and modeling as an alternative to the traditional high school senior math course. Steve, thanks so much for joining us tonight.
Thanks, Mike. I'm glad to be here.
And Bill taught high school math in a public school for 33 years. He's been a member of the adjunct faculty at Corning Community College, in Elmira College, and St. John Fisher College. A longtime T-Cube instructor, Bill presents frequently at local, state, and national conferences. And Bill is also a 2014 inductee to the New York State Mathematics Educators Hall of Fame and a 2018 T-Cube Leadership Awardee. Bill, we're lucky to have you with us tonight.
Glad to be here.
We're expecting a large crowd, so your audio is muted. Feel free anytime to send any questions to Steve or Bill using the Q&A window on the right side of your screen. We'll also be using the chat window to send general messages. As a reminder, the session is being recorded, and we'll provide a link to the event certificate of attendance at the conclusion of the webinar. We'll also send a link for the documents that Steve and Bill are using tonight. So do me a favor, and please try not to follow along with your handheld at this time. Just kind of sit back tonight, be engaged, and respond to the chat window when necessary. And then whenever you get the recording in a couple of days in your email, that's a great time to follow along at your own pace with your handheld. We hope you don't have any audio issues, but in the event that you do, try selecting Communicate from the top of the WebEx menu and choose Audio Broadcast. At this point, Bill is going to discuss our agenda.
Well, good evening. Mike's pretty well taken care of the introductions and welcomed everybody, but I would like to add my welcome. I'm glad you had some time this evening to come and look at a couple of interesting problems. The first one we're going to look at is a treasure hunt problem. And as Mike said, I'm going to encourage you not to try to follow along building the particular TNS file. You'll receive it later, and you can play with it all that you want to. Steve will then do some work with sectioning a cube in 3 dimensions. And really in between there, we'll probably take a look at some extensions to the treasure hunt problem that even extend that problem in many interesting ways.
Bill, thanks so much. And Steve is going to discuss our expected outcomes.
Hey, everyone, and thanks for joining us tonight. So our outcomes are as follows. We'll use our TI Nspire technology as a tool for involving students and you guys tonight in some inquiry. Primarily, we'll be using the construction tools and the transformation tools that are available in the TI Nspire geometry apps. And we'll also take advantage of some of the 3D graphing features of the Nspire to look at sections of a cube tonight and other kinds of prisms. So those are expected outcomes, and I'm excited to get going.
Thanks, Steve. Speaking of getting going, Bill, you have control. It's all yours.
Great. Let me get to the beginning here. Along the way, I'll share some of my favorite thoughts about tying into this particular problem, but also tying into just the classroom. This particular problem I've used in middle school, I've used it in high school geometry, and I've used it with adults, and pretty successfully with all. But it involves us to think about the problem situation and decide, is there any chance that there's even value in pursuing the problem? It revolves around a scenario of a treasure hunt. and we found a map. Describes the location of the buried treasure on an island. And the instructions on the map are as follows. From a single tree on the island, walk directly to the domed rock. Count your paces as you walk. Turn a quarter circle to the left, or counterclockwise, and proceed the same number of paces. When you have done so, place a stick in the ground. Pretty straightforward, easy direction to follow. Now return to the tree and walk to the spire-shaped rock, again counting your paces as you go. Turn a quarter circle to the right, or clockwise this time. Put another stick in the ground. Now, connect the sticks with a rope and dig beneath the midpoint of that segment, and you'll find the treasure. Would we all be willing to follow that map and find the buried treasure? However, slight problem has occurred. Florence has hit the island, and the tree has been washed away. Knowing this, is it worth your while to go look for the treasure? I'm going to give you a minute to think about that. I'd like you to decide and tell me in the chat window whether you are willing to go look for the treasure. Giving you a minute to think. When I call the word flamingo, I would like you to start typing in your response of whether you go on the treasure hunt or not in the chat window. Flamingo, who's going on the treasure hunt? Lots of folks are willing to take the plunge, go on the hunt. If you're not willing to, what would the treasure have to be worth in order to encourage you to go take a look for it? We do have an adventurous group because no one is concerned about the fact that the tree has been wiped out. So here's our domed rock, and here's our spire. But there is no tree. Where do you think I should start to pace off these distances? Again, I'm going to give you a minute to think about that. And when I say the magic word, you can type your response. Flamingo. So we're getting some interesting responses. Some people would start by proceeding to the dome. Others would proceed to the spire. And some are going to start from the midpoint of the segment between the spire and the dome. All of these would be worth pursuing, and I would encourage my students, of course, to try whichever they think is best. I'm going to start because I think today might be my lucky day. We're going to assume that my Inspire screen is the island, and I'm going to assume that the point where I stepped out of the island is where the tree was. And I'm going to follow my directions and see what happens. Again, the intent here is not for you to try to build this as we go along. There are many ways of doing this particular construction. You'll have a lot of time to play with this on your own. But the first instruction was to proceed to the domed rock. So I'm going to do that, and I'm going to mark that distance with this segment. And now I'm supposed to make a counterclockwise turn and proceed the same distance, and then put a stake in the ground. To get that job done, I'm going to use my rotation tool, and I'm going to rotate this segment about this point. And because I want it to be in a counterclockwise rotation, I want it to be negative 90 degrees. So I now have this point, me prime, and that's where I'm going to put my stake. Now I'm going to go back to my original starting point. Remember, my lucky day, this is where the tree was, I hope. And I'm going to proceed to the spire. And I need to do the same thing. This time, though, I'm making a turn in the counterclockwise direction. So I'm going to, again, rotate this segment, now about this point, 90 degrees. And put my stake. Does anybody remember now where I'm supposed to dig? Flamingo, where should I dig? Who remembers? Which midpoint? Ah, the midpoint between the two stakes. This midpoint right here. That's where I should dig. But digging there depends upon what? What had to be the case? A minute to think about it, and then I'll look for responses. Flamingo. Right, people are remembering. Teresa, Alina, yes. That's the place to dig if I stepped on the island where the tree was. What should I do in order to find out where that dig point should be if the tree had been located someplace else? Any suggestions to what I might do to test this particular construction? Is it worth getting my shovel and digging in that spot? So Alina says, move that beginning point. This is where I had hoped the tree was, but what if it wasn't there? What if I take this point? What if I had stepped on the island here? Or here? Or here? Or here? What if the tree was here? What if it was here? Anyone surprised? Is this result what you expected? Nice, Michelle. Yes, the red dot seems to remain fixed. A fixed point. Do we study any fixed points with our high school students? Why is the red point not moving, Chuck? Any ideas? It appears that no matter where I would have stepped onto the island, following their directions on the map, my dig point is a fixed point. We emphasize proof so much in our classrooms. But going back to Polya, the idea of guessing. I think now I could be motivated enough to look for a proof of why we have a fixed point here. But until I saw it, I'm not sure I would have tried to do that. When you get the TNS file, there will be a couple of pages. I'm not going to redo the construction here, but you'll be able to do the construction. You don't have to do it the way I did it. And if you don't want to do it, there is even a page that will be in the TNS file that will have the completed construction there. Some folks are suggesting that we move the spire and the dome. Nice suggestion. The way I constructed this, I have these points pinned, so rather than unpinning them, but that's a great extension that you can play with when you get the document yourself. We walk into our classroom saying, oh, today I think I'll prove that the hypotenuse squared is equal to the sum of the legs squared. That's not really the way mathematics is done. I think problem situations of this nature where we can play we can guess, we can be convinced, and then we can start looking for the proof. I'm going to suggest only one. There are more than one. I refer to this as proof without words. Because I encourage you to think of it as a proof without words. I'm not going to add any words. I do not claim that this is an original problem. If you Google the treasure hunt problem, you'll find a lot of references to it. And Steve, I think you have ready some interesting extensions that you've played with in this problem. I'm going to pass it to Steve.
Thanks, Bill. This is a great problem. So I'll wait for Bill to pass me the ball. I think it might have to go through Michael. We'll find out. But this is one of my favorite problems I used to use all the time with my kids when I used to teach geometry.
Let me see here, Steve. I'm not getting the ability to pass to you here. There you go.
You did it. Whatever you did, you did it. So let's see. So let me go up here and share my Inspire software. And so, so this is where we left off with a proof without words. And I did want to share a very quick. I'm just going to put it up there as a and give you a chance to take a screenshot if you'd like. So Bill presented this proof without words. And there's a wonderful, I think, very accessible complex number proof that I think it's accessible to students. And it should be when I think about what's in the Common Core state standards. So here are some things on complex numbers that high school students should be able to do. They should know that, you know, what the complex number is, and that every complex number has a form A plus BI, where A and B are real, and that, you know, the commutative, associative, distributed properties hold. There's also some things that they should do with complex numbers, such as represent complex numbers in the complex plane in both rectangular and polar form, and also represent addition and subtraction and multiplication and all that stuff also geometrically. And so I'm just going to place this next diagram up here on the screen, and if you want to get a screenshot of it, you can. But this is a these are for two fixed points where I think this was the spire, or maybe that was the dome-shaped rock over here on the right. I've located that at 4 plus 0i. And this is the spire-shaped rock. I've located that at negative 4 plus 0i. And this point down here is any old point, x plus yi. And as it turns out, this fixed point is at 4i. But the mathematics for this is really, I think it's easy to kind of follow, and I think it's something that is accessible to high school students. It's essentially, once you establish what these 2 points are, it's finding the midpoint of those 2 points algebraically by adding them together and dividing by 2. But it's neat that it doesn't matter where this point is located. There is no x and y in the coordinates of that point, that fixed point. So an interesting little proof. But again, if you want a screenshot of that, now's your chance, because I'm moving on in 3, 2, and 1. So I love taking problems like this and asking some what if not questions, which means by what if not, by taking an essential feature and perhaps changing it in some way. And so I'm going to give you guys a chance to do this very same thing. So here is my here is the problem that Bill shared. There's me. and there's this point, and there's this mystery slider. I don't want to mess with the mystery slider yet. But do me a favor. Wait for the magic word, which is flamingo. But think of some interesting what if not questions, where if you could change an essential feature of this problem, what would it be? And I'm going to count to like 30 in my head. So when I say the magic word, go ahead and enter that stuff in the chat window. But let's wait for a little bit, and I'll count to 30, then I'll give you the magic word. So if there was an essential feature to change, what would it be? And the magic word is flamingo. Something other than 90 degrees. Play with the slider. Just jump right to the slider. Different angles of turning clockwise or counterclockwise. Seems to be the big thing is what happens if you change the angle. Huh. Yeah, so someone suggested this. Let's see what happens. I don't know. Let's see this. So if I drag me around down here at the bottom, it kind of looks like that red point up there at the top where I'm supposed to dig is actually moving a little bit now. So right now both angles are 105 degrees. And it seems like, certainly seems like that point is moving. So what I did on the next sketch, I wanted to have a little bit more control over the movement of point me. So on this next image, I attached that point me to a line. That gives me a little bit of control of where this point is located. And right now, my two turning angles are both 90 degrees. So this point, as we recall from Bill's part of the presentation, that point is a fixed point. It doesn't appear to be moving. But if I were to take that angle and maybe make my turn angles smaller, and if I drag point me, it certainly looks like that point is moving in some way. I wonder if I could tip the line a little bit, what would happen? What do you think? How do you think that point is moving? You know, I'm kind of wondering, let's see, yeah. Seems to be following a parallel path to the me path. Seems that way. What's the, ooh, locus of that point at 60 degrees. So we should probably try a locus tool. So let me go up here and let me activate, let's see, construction, if I recall. And under the construction menu, number 6 is my locus tool. And so I click on the point that I want to create the locus. And then I click on the driver. And then I'll press escape to put that tool away because I don't want to make a locus of anything else. And it seems that that point moves along a line that appears to be parallel. Oh. I wonder what's special about that. And then as I drag my angle larger, oh, now it's behind me. Now it's in front of me. Okay, I'm having a little too much fun with this. I better move on. So my next question is I'm wondering about if in a line that point moved on another line, what do you think would happen if I attached the me point to a circle? Think about this for a second. Think about it, and on the magic word, go ahead and enter your answer in the chat window. So what do you think the path of that red point will be if I attach the me point to the circle? And So if I take this point, me, and I were to attach it to the circle, what will the locus of that point be? And your magic word is flamingo. So I want to redefine this point so it is on the circle. And as I drag this point around the circle, that point doesn't appear to be moving at all. But wait a minute, that's because my angle is 90 degrees. So let me change the angle to something else. You're right, when it's 90 degrees, we know that point will not move. And when I make it, say, 125 degrees, and I drag the M point, the me point, it looks like, well, I don't know what that would be. Let's create a locus and find out. So in my menus, I go down to the construction menu or submenu, and then I go to the locus command. Click on the point that I want to create the locus of, and then click on the path point or the driver point. Is it tangent to the circle? I better press escape and put that point away. If I don't put it away, I'll be making loci everywhere. So it certainly seems that, let's see, what if I drag, so there's a counterexample, Chuck. Oh. So I wonder at what angle would the circles be the same size? So at 90 degrees, there is no circle because it's a point. So at what angle do you think, and this is for the chat window, but don't put an answer in yet. Let people think about it. What angle should I set this to make the circles the same size, or the apparent circle the same size? So think about that. I'll count to 20 in my head, and then I will give you I'll give you the magic word. So what angle should I set that the slider to in order for the two circles to be the same size? And your magic word is flamingo. So 360, 180, 180, 180. Wow. I'll give it a try. So there's one. If I could only get it right to 180. Let's see. Can I? That's not bad. Not bad, kids. Not bad. And someone else said 360. Well, there's 270, 90 degrees in the opposite direction, and there is 360. Oh man, it comes back to itself. That is awesome. I did not expect that. So at 180 at 360, and at 270 it's back at 0, because if the angles are 270, that means we've made a 90-degree turn at both the spire and at the dome rock. And someone else, I think, suggested, it might have been Chuck, to suggest either 0 or 180. So 180 is yes, and if I go back to 0, it kind of pops right back down. So at 3 different angles, at 3 different angle settings, I get the same circle back. Oh man, great what if not. So I'm curious, and I'm not going to do this now, but this is certainly something for you. We attached this point to a circle, we've attached this point to a line, but there's no reason why you couldn't attach that point to some other shape or any other polygon, or perhaps even maybe a parabola or something else. And I'm curious what this shape is going to be. Is it always going to be maybe a scale copy of wherever that path is located? So one more extension, and then we will move on to the 3D stuff. I don't want to attach the point to anything now. I don't want to attach the point. I'm really just interested in what happens to the path. Focus on the red point. Focus on that. I'm going to make that puppy larger so there is no mistake. That's the point I'm talking about. Focus on the path of that point. So curious about a triangle. Well, we'll see if there's any time left. So focus on the path of that red dot. So make a conjecture. I can't tell if it's moving in a line or what the heck it's doing. And maybe I can move this somewhere not hard at all. So let's see. So let's take a. I'm going to keep dragging this. I'm going to keep dragging this up and down. Let's take a couple of minutes, people. And you're way ahead of me. So you guys keep. If you have an idea of what that path might be, go ahead and enter that in the chat window. I've got a lemniscape and some sort of an elliptical shape, perhaps. Oh man. So think about it. What kind of path do you think that is? Ooh, what if I put it way up here? What's going to happen? Oh. I could play with this all day long. Maybe that's kind of boring. I wonder what happens if I bring this together. Let's see. Oh. All right, ready? So I'm going to do a geometry trace. I can't do a locus because it's not being driven by anything on a path. So I'm going to select under the construction menu. Oh, no, I won't do it that way. I will do the right click, and I'll select geometry trace. And let's drag this puppy around and see what happens. Oh my. Oh my. This kind of goes back to Bill's quote from Siobhan Roberts in the King of Infinite Space. And it kind of reminds me, I mean, if it looks like an ellipse, it probably is an ellipse. What I'm really interested in is let me erase the traces. Let me erase my geometry traces. And I'd like to maybe move this point over this way some. And let me geometry trace this puppy again. So I will select a geometry trace. And then I'm just going to, oh man. This makes it worthwhile. This right here makes it worthwhile. That is absolutely, that is such a cool shape. I wonder where the foci are located. I'm assuming it's an ellipse. Guys, if it looks like an ellipse, it has to be an ellipse. I mean, conics just work that way. If it looks like a conic, it's probably a conic. So I wonder where the foci are located and how are the foci related to maybe where like the spire and the dome are located. Oh, man. I wonder. So anyway, I think we've milked this problem for about all it's worth, but I'm going to do one more. I'll move that point over here. I just want to see what's going to happen. Geometry trace again. Drag that up. Oh. Sorry, guys. Again, easily amused. The unexpected conics are the best kind of conics. When you don't expect them to show up, that is so cool. I am working. It's a computer view is what I'm working on. Someone asked, but it's a. But I'm on the software. But it's in the computer. It's in the computer view. I don't know if I can. If I change it to the handheld view, here's what it looks like in the handheld view. Oh, I got a geometry trace. And this is what it looks like in the handheld view. Another question that pops into my mind, it's somewhere along the line, this little dig line is tangent to this, what looks to be like a conic, and I wonder what that angle should be so that digging line is tangent to the conic. But anyway, enough of that nonsense. Let's move on to the 3D things. This is the other thing that we have planned for tonight, 3D, and we've got maybe about 15 minutes left, so we'll talk about this. So the idea for this, and again, you will get this to you from Mike. You'll be able to access this, and you can play around with this. I've kind of set this up in a couple of different ways. Oh, I did not mean to go to that file. I wanted to show you this one. The idea is to use the sliders on the left to tilt this plane around and create different cross sections of a cube or of a different type of a prism. Maybe in this case a prism that is 10 by 10 by 20, and even an application or an extension for high school students. So we'll talk about all of these here. So why is this important? Why is this important? Well, from the Common Core State Standards for middle school students, one of the things that they're supposed to be doing is they should be able to describe the two-dimensional figures that result from slicing three-dimensional figures as in plane sections of right rectangular prisms, in this case a cube, and right rectangular pyramids. So now we can graph pyramids in the Inspire software and the 3D software, but we can't really represent the cross sections very well. But we can do cubes and prisms because we can take advantage of the I call it a clipping box in the graphing app. And so the way this works is that there are 3 sliders. The top slider will tilt that plane around the x-axis, and you can kind of see where the x-axis is. Right there's the x-axis. It's moving kind of I don't want to say horizontally, but it's moving that way. And then the turn slider will turn the plane, and you can notice that the grid in that plane is kind of turning around the z-axis. So we have a turn slider, which will rotate the plane around the z-axis. We have a tilt slider, which will tilt that plane around the x-axis. And then we have another slider, which will move this plane up. The thoughts being is that if I was going to use this with a middle school class, it would be easier for them perhaps to manipulate the sliders rather than try to maybe manipulate equations or functions or things like that. So there are a couple of different cross sections that we can get. So it's certainly possible to get a single point or a line segment or a triangle. But parallelograms, trapezoids, pentagons, how could we possibly get these things? How could we possibly get some of those things? And so looking at the slider, I'm going to tilt this puppy as far up as I can. And then I'm going to turn that puppy up. Shape. Here's to be what kind of a shape? Not hexagon. What do you think? Do you think it's possible to get, this is for the chat window, do you think it's possible to get a regular hexagon? In other words, we've got a hexagon here, but the sides are not congruent. Would it be possible to get a regular hexagon? In other words, a hexagon where the angles are congruent and the sides are congruent. Take a couple seconds and think about that, and then maybe post a yes or no in the chat window for me. When I say the magic word, which is flamingo, can you get a regular hexagon? think so. Keep trying. Thanks, Chuck. In the process of keeping trying, I did create a pentagon. So here's my next question. If you can get this 5-sided shape, I'm sorry, buddy. Just pet my dog and laid down and missed him and bopped him on the head. Anyway, if I can get a pentagon, do you think it's possible to get a regular pentagon? Think about that for a second. I've got a pentagon. Do you think I could get a regular pentagon from using a plane cross-section? And a yes or no in the chat window when I say the magic word, which is flamingo. There's your magic word. Yes or no? Can you get do you think you can get a regular pentagon by a cross-section of a cube? It looks to me, though, like there's a lot of yeses and nos. This could certainly, I think a geometry fight could easily break out here if we kept going along this path. All right. And certainly I can get a non-regular pentagon, and I'm wondering if I can, I don't want to move this up too much more. I wonder if I could tilt it up, and that appears to be a trapezoid. I wonder if it's an isosceles trapezoid or if it's a non-isosceles trapezoid. So those are the kinds of questions that you can explore. I think there's 13 different cross-sections that you can get. And some that you can't, and some are, but this would be, I think, a useful investigation after perhaps you did some maybe styrofoam cube slicing, perhaps, or what I've used is like I get like those little blocks of butter and chop those up with a knife, and then make toast. Another thing for the middle schoolers, and again, of course, describing two-dimensional figures resulting from slicing three-dimensional shapes as in plane sections of the right rectangular prisms. So this is a 10 by 10 by 20 prism. The same tools work. What I've done here is I've just changed I've changed my axis settings. And so if I go to my range and zoom, and I go to my range settings, my X-min and X-max are both set to -5 and +5, same with Y-min and Y-max, but my Z-min and Z-max now go from -10 to +10, and that allows me to create the illusion of a box that is now 10 by 10 by 20. And the Inspire software has this, what I call clipping box, because it clips off everything, and you see nothing that is on the outside of the box. You only see the things that are on the inside of the box, and that is certainly a useful thing, but especially for something like this. So again, the same thing applies. This tilt button allows me to tilt the slicing plane around the x-axis until it's almost 90 degrees, and then I could tilt it back, and then I could turn around the z-axis, and there's a hexagon. And now that is true. So I think it's important, Chuck, that you kind of try to tilt the screen around to get a good look at what you're working with. So it would probably be best if I went back and reset this. On your Inspire keypad, and so right now, like from my visual, it looks like it's a square. But if I press the Z button on my keypad, I look straight down the Z-axis, and this is what it looks like from looking down the Z-axis. I actually see a square, but I would always see a square from this point of view, because even if I tilt the plane, I don't see that tilt from this point of view. But so there is a parallelogram. That is not a rhombus. And again, you can move this up or down, and you can certainly change the ranges of your sliders as well when you get this. So with the sliders, my intent is that this would be used maybe for middle school students or maybe students who are just new to the geometry app or the 3D app in the Inspire, and they would like to use some sliders to click on sliders. I think that's something they'd probably be used to. The modification for high school students would look like this. And again, from the Common Core State Standards, they should identify the shapes of two-dimensional cross-sections of three-dimensional objects and identify three-dimensional objects generated by rotations of two-dimensional objects. We're not going to do any rotations, but the modification is that high school students should be expected to change an equation of that plane, to move the plane up or down or to tilt the equation on their own to produce different cross-sections. So for example, this is a cube, and it appears to be, we could probably make the argument, and I think high school kids should be able to do this. A high school student should be able to make the argument that this is a rhombus because all of the sides of this cross-section, the sides, are all the same length. Because each side goes from, for example, one corner of the cube to the midpoint of one of the edges of the cube. But if I were to change this equation at the bottom, if I were to change this instead of x plus 2y, if I went x plus 3y and press enter, is it still a rhombus or is it now just a parallelogram that is not a rhombus? And if I change this maybe to 2x plus 3y, am I back to a rhombus? And is it possible, is it possible to get a triangle? I don't know what's going to happen. X plus y. Oh, is this is it a regular hexagon? I could see this as an application of when working with vectors. I could certainly see that. So I wonder if I could take the x plus y and maybe go. I'm going to try this just for kicks. Plus 5. And I've got an equilateral triangle now. And that is certainly one of those things. How can I create an equilateral triangle cross-section? And that's where you pass through the 3 vertices of your cube. And if I go plus 10, I don't know, I better go plus 9.9. I want to stop just shy. I guess I could go a little bit further. There's plus 10. I probably need to go even higher than that. So I think this is certainly something that high school students should be able to do, is kind of reason about the reason about the parameters of these equations. And this is one of the things when I taught freshmen who had Algebra 1 as 8th graders and did not move on to like Algebra 2 as 9th graders, which they do in my school. And so what we did with my students is I actually shared a document very similar to this. Because they were familiar with slope-intercept form, this allowed those students, though, to mess in a totally different kind of area, but still kind of make connections between what the parameters do. So, for example, if I change the x to a 3x, you know, it gets steep in a certain direction. What direction does it get steeper in? And there is not a regular pentagon, but that would certainly be cool if it was. So again, those are some things. I believe you'll get this file. If there's anything in this file that's missing, you can certainly shoot me an email, or you can certainly find me on Twitter. I've been known to. Have you guys heard about Twitter, man? Twitter is so awesome. I just found it. So anyway, I'm going to stop sharing. I'm going to hand this ball back to Mike because I think that's my part for tonight. So Mike, I hope you have some time left over here, man.
Thanks, Steve. And I just want to put your Twitter handle in the chat window. I think it's at GI Ohio, right, Steve? Thanks. So as we begin wrapping things up tonight, there's a couple things I want to be able to share available from our website, education.ti.com. If you move on to the Professional Development tab, and near the bottom are webinars. So we noticed that a bunch of you are joining us tonight for the first time. So if this is your first TCUBE Professional Development webinar, we're excited to have you here. Thanks so much for joining us. And if this is your second or third or fourth or more, thanks for coming back. Please feel free to visit our live TCUBE webinars link and check out all the webinars we have coming up. There's another one that's specific to the ATI Inspire coming up, I believe, towards the end of the fall here, November 27th. And then there's a bunch that are dual platforms, so both TID4 and TI Inspire that are coming up the rest of this fall. So free to check those out and register for any or all. All right, to receive a certificate of attendance, go ahead and click that link provided in the chat window. Also listed is a link for the documents, which I'm guessing you're probably going to be excited to receive tonight and play around with. If those links aren't working for any reason, just hang tight. You'll automatically get a follow-up email, and in that email will be a link to the recording, a link to the certificate, and a link to the documents. And if you're watching this on demand, go ahead and copy that link into your favorite browser to receive your certificate. If you're in need of any post-webinar follow-up, feel free to give us a call at 1-800-TI-CARES or send us an email at ti-cares@ti.com. We'd love to hear from you. Thanks so much, Steve and Bill, for everything you shared tonight. We really appreciate it.
You're more than welcome. It was great to have everybody with us.
Thanks, everyone.
Again, thanks for joining us. We hope to see you back online real soon. Have a great night.
Good night.